Okay, so I did some work here already, and I'm just gonna take you through these what I've done here. Okay, so the first thing you have to do to these questions, right? This is a decaying problem. So the formula is gonna look like this: A as a function of time, the initial amount, e to the power of my RT, but we know that R is going to be negative, or sometimes it's written as minus RT, assuming R and T are positive. Okay. So I'm just going to use RT, and trust me, R will come out as negative. Okay, and then what they're telling us that is this half-life information. So you have initially 100 for 100 to go to half of its own, initial amount, which is 50, takes this long. Okay, so I divide both sides by 100 to get half, and I'm trying to solve for this R. Okay. So then I take the ln of both sides, and I get this exponent is equal to the ln of half. So then R must be ln of half divided by 4.5 times 10 to the power of 9. But ln of half is same as minus of ln of 2. Once I have this value of R, I can write the full equation for the decaying formula. A is a function of time is, we know what this is, and we know what that is. So I've just substitute those values in there. Okay, and the part B, find the mass that remains after the sample after 10,000 years. Okay, that just means replace the T, okay, with 10,000, which is 10 to the power of 5. And of course, that'll reduce with 10 to the power of 9. And we get this. And now we just have to punch this in the calculator. Okay, when I punch this in, I get 99.998. Okay, 99.99. This makes sense. It takes for it to go to half, this like 10 to the power of 9. 10 to the power of 6 is a million years. 10 to the power of 9, right, is a billion years. This is 4.5 billion years. So compared to that, not much time has passed by. That's why it makes sense that there's still so much of it left over. Okay, part C, find the rate of decrease of the mass after 10,000 years. That's asking for dA over dt at 10,000. Okay, so we first need to differentiate this. Okay, so dA over dt will be 100 times by, if we differentiate the top here, we get minus ln of 2 over 4.5 times 10 to the power of 9. And we just multiply this itself, e to the power of ln of 2 over 4.5 times 10 to the power of 9 t. This can be a little bit simplified. Okay. Okay, so now do you see that the derivative is negative? This is always positive, so derivative is negative. And this makes sense because this is a decaying function, right? The graph itself will look something like this. So it's always decreasing. The rate of change is always decreasing. So what's left for us to do now is to plug it in, and this definitely requires a calculator. Right, so you plug in ln of 2, or actually it's just this right here, right? It's this right there, which is just these two parts, and you just times it by this again. Okay, you can do that, right? Or just punch it all in again. I'm gonna skip a step, but put 10,000 here. This is gonna become 10 to the power of, or 10 to the power of 5, so 10 to the power of 4. Okay. Scientific notation, we get roughly this much. It's very close to 0, very small value. So if you're to actually draw this graph, that means it's really flat. Okay, it's decreasing, but it's really, really flat.